everyone, so today I'm going to demonstrate two methods to find out which bacteria or which cloning host is transformant, which is non-transformant, which is recombinant, and which is non-recombinant. The first one is kind of cumbersome and uses the artificial plasmid PBR322, and the second one's easier and uses a beta-galactosidase releasing gene plasmid. I think this is also PBR322. So this is our PBR322 plasmid. Let me explain to you the different sites that it has got. So first of all, this is your PBU1 restriction enzyme. This is PST1. These are actually recognition sites, okay? Restriction sites actually, where the restriction enzymes will cut. So this is for PBU1, this is for PST1. Between PBU1 and PST1 we have ampicillin resistant gene. This is BMH1, this is SAL1. Between them we have tetracycline resistant gene. And this is our CLA1 and this is HIND3. And between them is your E. coli recognition site. This is your origin of replication, and there are some ORI proteins that are underneath the plasmid. Rope proteins actually, which help in the replication of plasmid proteins. They're involved in the replication of plasmid itself. Okay. So as you can see, this plasmid doesn't have any gene of interest, right? Now what I'm going to do is I'm actually going to introduce a gene of interest in this point right here, where my tetracycline resistant gene is located. And as I interest the foreign gene of interest, it is going to get inactivated due to insertional inactivation. Now this is my foreign DNA, and I'm going to cut a foreign gene of interest from this, right? Using my restriction enzymes. So this is my E. coli. As you can see, it has a specific sequence, right? It has a specific 6 base pair sequence, which is also palindromic. And only this can cut my foreign gene of interest at a specific location. And only the same kind of sticky ends will facilitate the action of DNA ligase. It will stick only if the sticky ends are of this kind. Now let's say I was using another restriction enzyme such as HIND2. Now if I were to cut using HIND2, I would get a different sequence of sticky ends, as you can see. So if I cut using HIND2, I get a different sequence, and as you can see clearly that these sequences don't match. The sticky ends are clearly different. So I have to cut both my gene of interest and the plasmid DNA using the same restriction enzyme which I used to cut the foreign DNA. Do you get it? So these are two different restriction enzymes. This is my E. coli and this is my HIND2, and they're both like molecular scissors and they cut differently. As you can see, this one cuts a certain sequence, 6 base pairs palindromic sequence, GAATTC. This one cuts a different 6 base pair sequence. So that's why I need to use the same gene. So once I'm done cutting both my gene of interest and my plasmid with the same molecular scissors or the same restriction enzyme, I can insert it into one particular point. Let's say I inserted it into the tetracycline resistance point. So now let me show you what happens. Ta-da! So here's our gene of interest. I have sort of highlighted it or stained it to make it more visible, right? So this is our gene of interest, and using DNA ligase, I have actually attached it to our plasmid, and this is our recombinant plasmid. And as you can see, it has lost tetracycline resistance due to insertional inactivation, but it still has PBU1 and PST1 and ampicillin resistant genes. So this is our recombinant plasmid. Now let's introduce this into our host. So this is a bacteria, and I'm going to use my plasmid. I'm going to introduce it into the bacteria using the one of many techniques that exist. Also, you could use another cloning vector, not host. Cloning vector known as bacteriophage, which has a very high copy number per cell. I could introduce my foreign gene of interest into the bacteriophage and also introduce this bacteriophage into our cloning host. But at present, I'm using a plasmid. Okay. So this is my first plasmid which has my gene of interest, which I want to multiply, right? And I am going to introduce this into the host, and it went into the host. Okay, so it's not as easy as I showed, but yeah, I did introduce it into the host. So this is my perfect plasmid which I want to replicate. So this is my first host which is transformed with my plasmid, which also has my gene of interest. The second host, on the other hand, unfortunately got transformed with a plasmid which did not have my gene of interest. So it still has tetracycline resistance, it has not lost its resistance, it still has ampicillin resistance, but it doesn't have our gene of interest. So this is not the plasmid that we want to replicate, but I don't know right now. I'm a biologist, I can't see this with my naked eye, so I'm going to find out using an experiment. But right now this is my second bacteria, second host without the gene of interest. And the third one sadly did not get any plasmid, it did not even get transformed, it's a non-transformant, it doesn't have any plasmid, my plasmid could not enter it. So these, as you can see, are my three different hosts. Now I'm going to do a plating, right? And then I'm going to find out which one is which. So as a biologist, you don't really know which one has which one is non-transformant, which one is transformant, and which one's non-recombinant and which one's recombinant. You don't know. You have to find out using an experiment. So here's my plate 1. This is what Cohen and Boyer did as well. So here this has ampicillin gene. So this has an ampicillin antibiotic. Antibiotics essentially are meant to kill bacteria. So if a bacteria does not have ampicillin resistance, it will die. Okay, so now let's bring in our 3 bacteria.